Why do we split the data? Imagine a teacher gives students the exact exam questions to study. On the exam day, the students scored 100%. Well, if we ask, did they actually learn or did they just memorize the answers? Welcome to day 2 of the Module 5 for Foundations of Machine Learning. We're going to talk about train and test splits for linear regression problem. And we're going to start with why do we split the data? Take, for example, if you train a model based on a particular data so that the model understands the data point and the patterns are in the data. Now you use that same data that you used to train it. You use it to test it to evaluate if the model performs well. Merely looking at it from afar off, it is not efficient because you are just typically giving it what it has seen before and it's going to get it 100%. It's going to absolutely get it. So this is a major problem that exists. It's the same problem that exists in machine learning. So if we train a model on all our data and then test it on the same data, it will look perfect. Well, it has just memorized the data. It has not learned any real patterns. So what can we do to solve this problem? That is where train and test split of our data set comes into play. Train, test, splitting of our data set. So we split the data into two sets before training. The first one is training set. Usually we have it around 80% if we have a lot of data set. The model learns from this. Then we use the remaining 20%. We use it to evaluate the model. The model in such a way that it has never seen that data point before. So the test set is like the real exam. The model only sees it after training is complete. So during the course of your time in school, you have a time where you just go to a classroom, get a lot of teaching lectures. Then there's a time for test, right? Most of the time, whatsoever comes out in the test is just similar to that you were taught during the class. But it's not, most of the time, it's not the same thing. It's a little bit different just to check your knowledge on the pattern that the teacher is trying to teach you. So this is just an analogy of what train test split means. So you would ask what 80-20%, 80-20 rules. It's a common default. When you have a very large data set, 80-20 is very recommended, highly recommended. But when you have little data, you want to have 90-10 because it takes a lot of data to train your model. So the key principle is always the same. The model must never see the test data during training. Now let's go over on linear regression. Linear regression is the simplest machine learning algorithm. Simplest ever. I'm very sure most of us have heard it. A linear regression. When we took our mathematics class, we did a linear regression unknowingly. When we had that y-axis and x-axis, we drew on the our Wirac and Echo when you were writing your mathematics first exam. You were told to plot a line, a straight line, using a y-axis and an x-axis. Yeah, you are typically doing a machine learning You are developing a model unknowingly. So that's a good news. Every one of us has developed a model before. So now it's a good time to put it to use. So ML algorithm, linear regression as the simplest ML algorithm is just fitting a straight line through our data set, not a curved line, just a straight line. You remember y is equal to zip c plus mx? Yeah, the formula for plotting a straight line. So let's go over a visual example. But before then, let's explain. Imagine plotting quantity on x-axis and total sales on y-axis. I believe that should be, yeah, that should be linear. If a quantity is on the x-axis and total sales, because the higher the quantity, the higher the total sales. So each dot is one transaction. So linear regression draws the best fitting line through all those dots. We will see that very shortly. So once the line is drawn to predict total sales for a new transaction, you must find a quantity value on the x-axis, go straight up to the line, read off the total sales value on the y-axis. Don't worry, we'll show you what the diagram looks like. If you remember that formula we used to say y is equal to mx plus c. So this is the c, this is the constant, is an intercept. Intercept is a starting value. Take, for example, put every other value of our variables to be 0. That will give us the intercept. So that's the starting value when all inputs are 0. So the formula for linear regression is when we are trying to predict total sales will be equals to, this is a constant intercept when every other values are 0. We now add it to, this is a coefficient for the first variable, coefficient for the second variable, then you multiply the coefficient with the input of the variable, such that this coefficient is such that a unit increase in that feature it tells us how much the total sales is going to increase if we increase this feature by 1 unit. This gives us the coefficient, it shows how powerful this feature is. So if you have a big number here, that means any unit increase here will result in a very high upward movement in total sales. So that's just a simple mathematical expression of what linear regression does. So the algorithm finds the value. What the algorithm does during the training, it finds the value of our coefficient that makes the line fit the best fit as closely as possible. The best fit for the data as closely as possible. I'm not expecting you to grasp this very early on, but just remember there are coefficients and there's an intercept in a linear regression algorithm. The intercept is here, the first one, and these are the coefficients of the formula. Another thing we need to understand is that regressions have assumptions. So it's not every data set that you can run a regression on. The first assumption is linearity. So you want to make sure the relationship between the input and output is almost a straight line because you want to draw a line, a straight line of fit, the best fit. So if you are trying to model something that doesn't move in a straight line, then we will be doing the wrong thing. So the first thing is check for linearity. This next one is it independent? The values of the features, are they independent of one another? That is, does price per kg, does it is it independent of quantity per kg? So one row, we want to make sure one row's value does not affect another row's value. That means it's independent. Usually our target variable, this is aside, so but just notice our target variables are usually dependent on the features, one or many of the features. So, but we want to make sure our features are independent. So, and we want to make sure we have a normal distribution. When you plot your data on an Instagram, you want to make sure that they have a normal distribution. Uh, that means they are spread. The spread is normal. And you want to have a normal error. The mistake the model makes are roughly bell-shaped. So you want to make sure when the model when your model produces a result, the error that comes from the model, when you plot it on histogram, it is bell-shaped. That is, it's normal. So all of these are the very important assumption the test to make to be sure that a linear regression approach is good for a particular data set that we are working on. So how do we measure regression performance? The first one is mean absolute error. The mean absolute error takes the average size of the mistake, ignoring the direction. So sometimes our error could be negative. That is, how do we get the error? We get error through subtracting the actual prediction from the actual data point minus the prediction, the predicted value versus actual value. So you minus actual value from the predicted value, then you get your error. But some of the time, if your actual value is greater or less than the predicted value, you could get a negative. In that instance, that's why we use absolute. Absolute is how we use it to eliminate any potential negative that we have in our data. So let's take, for example, if our actual value is $1,000 and the predicted value is maybe 1,500, that means we have a negative 500 in our error. So put that into an absolute uh, value, then it will become 500. So we say at that point our MAE is 500 because the model is off by 500 on average. So this is very easy to interpret because it maintains the same unit. There are others like root mean squared error that does not maintain the same unit because we are going to square it. And so similar to mean absolute error, root mean square error actually penalizes for large errors more. A very few A few very wrong predictions will push a root mean square error up more than MAE. Since we are squaring the error, so if we have a large error, say if we compare, let's compare it. If you have maybe your actual value is 500 and your predicted value is 501, so you only have one as a mean absolute error. Now, but in another instance, if you have your actual value to be 500 and your predicted value to be 1,500, that you have 1,000 mean absolute error, then you're going to square it again. So imagine comparing it with the earlier one that we get, one as a mean absolute error, square it and compare it to 1,000 mean absolute error, then square it. So the purpose of that squaring it is to make sure that anytime we have a large error, it penalizes it pretty aggressively to make sure that the model or our evaluation, we evaluate a model that is really not having a lot. When we evaluate the model, we pick the model that does not have a real large error. We want to avoid large error. So that's why we choose root mean square error. So we call it similar to MA penalize large errors if you run okay. So R squared, coefficient of determination. So this answers what percentage of the variation in the target does the model explain? R squared is another way of evaluating our linear regression. It actually tells us if our model is good or not. I think that's one of the best evaluation method to use for linear regression because it tells you how well our model is performing. Um, when your R square is 1.0, that means we are overfitting because at that point we do not have any, the model is predicting all of it pretty good. So we may have a problem at that point. We don't want it to be too much, but we don't want it to be too low either. So when we have R squared to be 0.0, then the model is not, it's not good. It's not just better than an average guess. So when you have R squared less than 0, uh, is worse than predicting the average. That means something is wrong. So which metric matters the most? It depends on the problem. Like I said earlier on, if large errors are very costly, if you want to magnify large errors, use your root mean square error. But such as in medical dosing, you want to reduce your large error there. So if all errors are equally bad, use mean absolute error. But remember to always report your R squared because it gives you how well your model is performing generally overall, not only based on the error, but generally how much prediction is getting right, how is performing overall on our model. So let's just look quickly on how to do regression analysis. So remember we have our data, so we can put it in a DF here. So and here we have a label encoder. I don't want to go too much into this, but this typically helps us to convert textual values into numbers. You remember we have numeric values and we have categorical values. Categorical values such as the one that we have in the city, Lagos, Ibadan, blah, blah, blah. And compare, we want to make sure these textual values are converted into numbers. So this particular encoder encodes text into numbers. Numbers are easily understood by the computer and they use it, it's easy for operation. As you can see, it will help to um, transform the products. The first one that we use is the product. And we establish another feature or variable on our data set, and we say, okay, this label encoder, try and fit transform it. Try and fit transform our product into numeric values and save the output into product encoder. The same thing we did here, label encoder, but here we did not use LE, we just use label encoder as you can see, but we can use LE as well. Dot fit transform our city and put it into city encoder. So if we try and check for, let me see, DF, let's see what happens. You will notice that our product encoder now has the city is city encoder. Lagos should be 4. Anytime we see Lagos, it should be 4. So Lagos here is 4. Lagos here is 4. And if you notice, the product also has been encoded. Anytime you see beans, it should be 0. Look at it. Anything 0 is should be beans. 0 beans. So that's typically what an encoder does. It's important to encode because we want to run a machine learning algorithm. Just remember that. So the next one is to define features. Like we talked earlier on, we want to define which one do we want to use for our features, like the input, and which one do we want to use as target. So this depends on the problem statement. From the problem statement, we want to predict the total sales, right? So the total sales should be our target column, as we have here. So which is the Y, is the target column, and here we have the X, which is the feature columns. So that is pretty much that. So if we say X, I believe if we say X, run this cell and say X, we should have it here. So we have quantity, price, product, city. So we have these ones here. Remember, we removed the categorical values, right? We replace it by the encoded values. Now, after doing that, we have our X and our Y. If you also check for Y, you should have Y to be this, the total sales, right? So since we are moving in the right direction, we already have our target, we have our features separated into X and Y, right? Now we want to split. You remember we need to split so that before we can train, we need to make sure we split our data. Uh, Typically, we use 80 and 20% as we talked earlier on. And we usually choose a random state so that next time if you want to reproduce this type of analytics or algorithm, we just use the random 42. Remember, random 42 just to be consistent with our operation. So the test size here means 20%. This 0.2 means 20% to be the test size. So this is the typical syntax for splitting our data set. For training, this is X train, that means X train, which is the feature training, X test, feature testing, Y train, this is for our output, our target training. This is for our target testing. So make sure you remember that because during the evaluation, we need our X test and Y test so that we would be able to use it to compare uh, what the product is, I said the product, I meant what the model is talking about. Is it really what it is? And to evaluate the model, that's what I meant. So we need our Y test and X test to evaluate the model. Remember that. Mhm. So we can print, let's try and print this. So from what we have 793 for training, and testing, we have 199. So anytime you want to do test and train, you can just copy this code here. It will split the data set for you automatically. So now we're gonna create the model and train it on the training data. I would give you a major news. The training of data using an algorithm, it's one of the simplest and the easiest thing to do because it's just two or three line of codes as you have seen on the screen here. The most important thing, as we said earlier on, is cleaning the data and making sure that it is well prepared for uh, machine learning algorithm. So to create a model, you just need to call a model. You remember we have our linear regression already that we called here in our model. You see here linear regression, so that is what we are calling here. We already imported it here, and now we are using it here. So now we call it and we assign it to the name model. So now anytime we call model, we say model is going to refer to linear regression in this cell for the purpose of this course, right? And not only this cell, even outside this cell. So model, you remember we put linear regression as model, right? Now we are using linear regression dot fit. Now we put our training sets here, y and x. Remember, the model learns from training data. Then now we want to predict model dot predict x test using the result. We want to predict result of our model that we have trained. We want to predict using x test. So now as soon as we run this, we already have it in here as y predict, right? So now we want to calculate how far off the predictions are from the actual values. Remember, we have our y prediction already in y underscore prediction. Now we want to calculate our error. So you call upon mean absolute error. You remember we have it over there already in our modules. So we want to, the y test, we want to compare it to y prediction. The y test, we want to compare it to the predicted values. So now we have our, here we have our average absolute error. So here we have our R squared. So this is how you get your R squared. So all of this, if we print it, so we have our mean average error to be 3,287. Then we have our R squared. That means that the model was able to explain 91% of the data points clearly. Yeah. Quickly, let's show us the charts to show how a linear regression operates. So we have the actual total sales here and the predicted total sales. You see this line here is the model, the predicted model. So all the rest here are the data points. Any data point that is close to this shows that the closer the data point to this line, then the closest the model, the better the model is predicting that data point. So if you see a data point very far, that means the model is having a large error here, like you can see this. But for all these ones, that means the model was able to predict them very closely. That means the mean absolute error will be very small. But the ones that are far away, it's very large, very large. So here is the prediction of the model. This is the linear regression line, and these are the data points that is trying to fit. So you see here, dot close to the red line is equal to good predictions. Look at the chart above. Each dot is one transaction from the test set. The x-axis is the actual total sales value. The y-axis is what the model predicted. The red dashed line is where the actual is got to predicted is perfect. So dot close to the red line is equal to accurate prediction. Dot far from it is a large errors. So the R score tells us how the model fits. An R scale of 0.85 means the model explains 85% of the variation in the total sales. The remaining 15% is noise or factors not in our features. So the higher the R scale, the better is the linear regression model able to understand the pattern in a data set and is able to fit in the best line to explain what the reality or the dynamics of our total sales. To think about it, what other columns of information might help the model predict total sales? This is just a thought. You can think about it. What other data point can we add to this, to our features that will make the prediction to be much more accurate? In this case, please, you have a practice question here. Go over it and let me know what you think in our WhatsApp group. If you have any question, just post it there. This will be the end of linear regression, and I hope to see you next in the next lesson. Thank you.